So these are bar charts, and they are different from histograms because here we can choose the size, the size of the bin or the number of bins. In these histograms, we will see this in a moment. One can choose how many bins we want to have, into how many bins we want to fragment the whole data set. And usually there would be an equal size, right? So here we have, so we have a time scale from 0 to, I don't know, maximum maybe here 10,000 or 12,000, something like this. And each bin has the same size. Of course, one can also imagine that these bins have different sizes, or one could log transform the scale and have different sizes. There are different ways how one could do this. And here the bins are, so there's actually no bins. The categories would be the bins, right? And then the bar chart would count how many occurrences we have on average in each of those categories here. So this was another example that we had yesterday. So while we have here the different tasks and the production duration, here we have normalized typing duration per word and the different texts. So we can look into this data from different angles, so either from the participant or from the text. And here this is a slide graph that we also looked into yesterday, where we can see that different texts may require different amount of times, even when normalizing this by the number of words. Okay, so these are bar charts. And then we have box plots, like this one here. And box plots would show characteristics of the distribution. So here we have a distribution similar, well, and then we have, so this represents the entire data set, and this would be 1/4 of the data. So each of those things would be 1 quartile. So this would be 1/4 of the data. This would be another quarter of the data. And then we have this first quartile, and everything that goes, data points that go beyond 1.5, these interquartile range, would be outliers here. Okay, and so this is the median. So this is the middle of the data set. So yeah, so we have the same number of occurrences or data points on the left side and on the right side. And so we can see somehow a distribution of the data. For instance, something like this here. So if we have a more or less equal distribution to the left and the right, a symmetric distribution, then this box plot will look quite regular to the left and to the right. And then we have here something, a data point that is a bit further away, 1.5 further interquartile ranges away. That would be considered to be an outlier. Or if we have a skewed data set like this one here, we can see this also in the box plot. So the median would be around here, okay? And then the skewed data set, we would have a longer widget here on that side, and then we have a couple of outliers here. Okay, so it represents the same. So depending on how which visualization you prefer, here of course you can see immediately what is the median, and you can see similar things like in the histograms, but with a little bit more systematic plotting of the median and the outliers and so on. So here it compares. This slide compares the box plots and the histograms. So if this is exactly symmetrical, then the median is exactly where the average so this would be the same. This is the median, okay, and it would be symmetrical to the left and the right side. Here you would have a skewed data to the right, and here to the left. Okay, and then, but what can be hidden in the box plots is, for instance, instances like this one here. So you have two, maybe quite different distributions, but the box plot would represent the two data sets in the same way, right? So the median would be here, and then you would have the same interquartile ranges here, you would have the same outliers here and here, but the distribution of these two data sets looks different in a histogram, but the box plot would show this in the same way. Okay, so again, yesterday we looked into some box plots from the translation sessions, and we can see here that different participants have different amounts of typing time, or have different typing patterns, if you like. This P19 here on the median is most elevated from all of them, but the variation is also much higher here. You can see, you know, that some of the data sets was very quick, and some of the data sets took much longer. So this P19 has a much higher variation than, for instance, this P20 here. Okay, but for all of them, you can see that the data set is a little bit skewed. Yeah, so they have the median is in the lower part of this interquartile ranges here. So something like this you can easily make out. Then there are similar plots, but some argue that this is called a violent plot, and some say you can better see what the data looks like. So this is again apparently the same data sets, and once it's represented like this, with a big belly here and a slim belly, if you like. And I don't know, it's maybe a matter of taste whether you can more easily understand visualization with box plots or with violin plots. But we can have all these representations, all these visualizations are similarly difficult or easy to produce with Python. Okay, now if you look into the box plots and this normal distribution, right? So where we have this shape here of the bell shape, which is very symmetrical towards the left and the right. So we would see that the interquartile ranges, we have here different values. We have so 50% of the data falls into these between Q1 and Q3. So this makes out 50% of the data. And then this interquartile, if you go 1.5 interquartile ranges towards the left, then we are at 97 or so percent, right? So this covers 97%, and everything that is outside here, the data points outside here, would be considered outliers. And this, if this is a normal distribution, fits quite well the definition that is often used in statistics, where we have here so the mean would be identical to the median. Yeah, so in this case, this is the median, and this would be identical to the mean. The mean is here in the middle, right? And the median is in this box plot here. And then we have the variance, or the standard deviation is the square root of the variance here. We can see that here one standard deviation, or that in almost 3 standard deviations, as you can see here, almost 3 standard deviations would be the end of these box plot widgets, right? And so that's often assumed to be also a criterion for outliers. So it's here it says 99.7%. 3 standard deviations is covers 99.7% of the data. So the amazing thing in this normal distribution is that we actually only need 2 values to represent the distribution, and that is the mean and the standard deviation. And with these 2 values, we can then characterize very different kinds of distributions here. For instance, we have the very pointed distribution here, where we have a standard deviation of 0.2, or we have a very flat distribution here, the yellow one, where we have a standard deviation of 5.0. Or then we can say, okay, so the mean is shifted towards the left and the right. So the amazing thing is that we can classify or characterize distribution by only these 2 values here. Okay, now, so this this basically describes a single variable, right? So the distribution of a single variable with the histograms, box plots, or bar plots and so on. But we can also put into relation 2 variables and correlate 2 variables, or have a linear regression or some other ways of relating 2 variables. I want now address here correlation. So a correlation of 2 variables can be positive, as you can see here. So we have 1 variable on the horizontal, 1 variable on the vertical, and then they can correlate very strongly positively, or they can correlate negatively, or they are basically uncorrelated, as in this picture here. Okay, then so they can correlate strongly, as shown here, or moderately strongly. So this would be strong correlation and positive. This would be moderate correlation and negative. You can already see by the points, if you put in a line here, yeah, you see that these 2 variables are correlated here moderately, not so strong as this one, but negatively. Here, they're basically unrelated. So whatever is the value of the 1 variable, it doesn't say much or anything about the value of the other variable. Or here you can see that this is a nonlinear relation, right? So whereas these relations here somehow are linear, this relation doesn't seem to be linear, but nonlinear in a way. Then also what we already had previously here, we can guess that there are maybe 2 that what we plot here on the x-axis, right, is actually 2 kinds of clusters. One around here and the other one there, and the so this is a kind of a bimodal distribution. Or here we can see that maybe there is some data missing. We don't know whether this is a linear relation or a non-linear relation. And then we can also see in this distribution that there are outliers. For instance, we can see here there seems to be quite nice, strong negative correlation, but we see some outliers. So there are some data points that don't seem to be really on that line here. Okay, so that's what we can see with scatter plots. And also here we can put not only 2 variables, but 3 variables, for instance, by having a different color here. And we had something similar yesterday, also yesterday here, where we have the number of insertions per text. So again, it's from the same, it was from the same text, right? It was a whole session text, and there were so many insertions in the text and the typing duration. And we can see here, so there seems to be a relation somehow, but for each of those different tasks, a different relation somehow. And this can then be, well, we present this on the same graph because they all have a number of insertions and a duration, but you see that those points are differently distributed and they seem to follow a different logic or a different relation for these three tasks. Okay, any questions or comments or doubts? Okay, so here we can just visualize these relations. We can also quantify the strength of these relations. And also this we addressed yesterday a little bit. One is this person correlation coefficient, where we have here a covariance. So this is the covariance of the two variables x and y divided by the standard deviation of x and the standard deviation of y. And here, so what this means is that basically from each value we subtract the mean, okay, for the mean of the x and the mean of the y, which means we shift this whole distribution over the 0 point. And then this is the multiplication of these x and the y points and the sum over it, and divided or normalized by the standard deviation. And this gives the value between -1 and +1. So a -1 would be a negative correlation, and a plus and a positive number would be a positive correlation. And if there is no correlation like this one here, that would be a very weak, that would be 0, a value of 0, something like this. And then, yes, so people call this, instead of giving a number between -1 and +1, they also give it a natural language expression like weak positive correlation or strong negative correlation, and so on. And what is considered weak and strong correlation is very different in the different scientific areas. So if we have here, okay, so perfect correlation would be, of course, a 1 or a -1. And then if we go into psychology or sociology, perhaps, a strong correlation would be 0.7, moderate until 0.4, and then we would have 0, weak correlations, and so on. Here in politics, they seem to have more categories, and I guess in physics, they still have very different kinds of categorizations. So, but for what this, I mean, if we gather this gaze data, for instance, and we get to see a correlation between behavioral measures, then seeing some kind of correlation, very strong correlation, it would be very rare. So we don't expect to see very strong correlations because the data is just simply very noisy. Okay. But yeah, okay. So here then we can also show these correlation, and this is something I want to show in a moment. In an R, sorry, in a Python notebook. So we can see the correlation between insertions and deletions. Or, yeah, so means how many insertions someone produces and how many deletions someone produces, and then what is the correlation between insertions and a normalized version of it, and different ways of normalizing it. So we can put this into a correlation matrix, and as you can see, the correlation here is symmetrical. So these values here are always identical. So yeah, so you can actually flip over this triangle here and you get the same number, because if you correlate this feature with this one, or you correlate this one with this one, is basically the same thing, right? So that that is symmetrical, just flipped around, and this is different in a regression analysis, where this would not be symmetrical. So if you have a dependent and an independent variable in a regression analysis, this is not symmetrical, but in a correlation, it does not matter in which order you put the variables. They will show the same correlation coefficients. Here is another fancy graph where you can see, again, here is the same. So this correlation is the same, it's just flipped over. And here you can, because in the middle, you will always have, as you can see here, if you, so the correlation between insertions or deletions here is always 1, right? So there's always a sure correlation because the same variable correlates with the same variable, of course, to 100%. And because this is just has no information, we can also use this middle diagonal here to show the actual distribution of these different variables here. Okay, and here we can also see that we have actually well, one measure, but different categorical variables here, which are shown, where the distribution of which is shown here in these in this middle parts here, and here in the sides you can see the correlation. And of course, you could also quantify this and put a correlation number, how well those correlate. Okay, so one thing to know is that correlation is not causation, right? So we can correlate any two things. Any two things we can correlate. If they share some features, we can correlate the stuff. All right, but that doesn't mean, and if there's a perfect correlation, it does not mean there is a causation. And this is sometimes a little bit difficult to figure out what is actually a causation or a correlation. But here, this example is that both ice cream sales and shark attacks increase when the weather is hot and sunny, but they are not caused by each other. They are caused by good weather, with lots of people on the beach, both eating ice cream and having a swim in the sea. Okay, so ice cream eating and shark attacks are not causally related, but there's a very strong correlation, as you can see here on this graph. See, a similar thing here, sunburn and ice cream correlate, but the causation is the hot weather. So because there's hot weather, people use sunburn, have sunburn, use maybe sun cream, and the sun also causes people to eat ice cream, but there's a correlation between these two instances, but the reason the causation is somewhere hidden behind these behavioral patterns here. In summer 23, so there is these two Python notebooks. This one here I talked about yesterday, and this one here is I would like to talk about now. And well, similar structure as yesterday. So first we have here, we import a couple of libraries, pandas again for these tables, these nice tables here. NumPy is mathematical, so with lots of mathematical operations, and this stuff here is for visualization, and this is for language linear regressions. And then again, this library here, which has this particular function to read data from that TPRDB. And again, this function here, this TPRDB read TPRDB tables, takes here a list of tables that are supposed to be read, and here a path to the user or to the TPRDB, and this path is data CRITT TPRDB, and then the user in this case is ATA22, and in this user we have a couple of studies. I can maybe just very briefly show this. So again, you can type here, this is the user ATA22, and there are a couple of sessions that we had an experiment recently with ATA. ATA is American Translator Association, and they have exams for translators to translate texts from, I think, English into a couple of languages, maybe also the other way around. But here we have an English text into Spanish, and the other experiment is from English into Arabic. And they're not so easy, I think. So these are texts, source texts, which are designed to have some difficulties to test translators, whether they get the certificate. And we use this this text for some experiments into Arabic and into English with different translation briefs and so on. But this is not the point right now. I'm just using this data, and it was recorded in Trados with an eye tracker here. So these are, each of these segments that you can see is a Trados segment. So we pasted this into Trados, and this is from scratch translation with different translation briefs. But anyway, so this is the data, and we have this for Spanish. So this would be English Spanish, and this would be English Arabic. So we can actually load any number of studies here into one table, segment table here. And this parameter here would indicate what table we want to load. And as we already explained a couple of times, we have about 10 or 11 different tables, and this SG table here would be a table that summarizes segments, so the data on a segment level. Yesterday we looked at the session level, so a whole translation session was summarized in one table. This one here looks into a segment, so we can load this data here and show the first 10 lines. So this is the variable segments that contains now how many? So there's 8 sessions in for Spanish and 14 sessions for Arabic, and these 8 sessions have 94 segments, and these 14 sessions have 164 segments, and each of those, what is it, 258 or so, if we add those together here, there would be 258 lines in this table, and each line represents one segment. Okay, again, here we have just a number from 1 to n. This would be the name of the study. This is the name of the session, and it's English into Spanish here. Then we have the task, which is encoded in the session name. This is task is translation here. Yesterday, for what reason, I don't know, we had true here, now it shows T. This is the text, So we have, I think, 4 different texts. So this experiment consisted of 4 different texts. This is all sessions from text 1, and there should then be text number 1 to 4, or whatever number of texts we have different. So this is the participant. So this is basically a decomposition of the session name. So that's why these session names should follow that coding advice to have these right columns here. To know we want to compare maybe translation sessions of the same translator and so on. So that's why this should be consistent in a way. Okay, so then we have here. I can maybe also put here 20, and then we can see here that there are 11 segments in table in text 1, and then we have text number 2, and we have a segment 1 to n in text 2, and so on. So the difference here, this was recorded with Trados, right? And in Trados, each segment, so remember we had this thing with translog where we can merge 2 segments, for instance, 2 sentences on the source side and align it with 1 segment on the target side. This is not what happens in Trados. In Trados, we have the exact blocks in the Trados interface already. So the number of source text segment and target text segment will always be identical in Trados. This is not the case necessarily in translog. Here it shows n edits, so how many times this segment was edited, and that means, so because we have here translation from scratch, each of those segments was edited once, of course, no, otherwise we would not have a translation. And this segment here was edited twice, means the translator edited this, then went out, again, went to another segment, and then came back and activated this again. So this was edited twice. Here we have the duration, the total duration. So that means the sum of these 2 editing operations in the segments amounts to this number of milliseconds. And this fdur is a duration that takes out pauses of 5 seconds or longer, which we don't have. No, all these numbers are identical. So the translator did not stop to produce. So there was always data collected with no interruption of more than 5 seconds. Then we have a number of these pause metrics that we, I think I will look into this in more detail tomorrow. But the idea is that we will have stretches of typing and stretches of pausing. Right, so we already, if you remember, we had here, if I go back to this graph here, and we show these PUs here, production units, then we can see that these are production units, and then we can put the TU lines too. We already had this a couple of times, I think, right? So here we have stretches of typing and pauses, okay? And in this graph, a coherent, so we call this this gray bars coherent typing, okay? So in this stretch of time, you can zoom in there still a little bit more if you like. Here, okay? So these black dots are, of course, typing event keystrokes, okay? And here we have a coherent kind of a typing, which is visualized here as this gray box. And then there is a little pause here, and this pause is more than 1 second. So this box here, of course, there is a pause between every successive keystrokes, right? And then the question is, how do we define coherent typing. And here, this is the definition is that the if the pause between successive keystrokes is less than 1 second, then it's considered to be coherent typing. Means that every time we see a blank here, so this one, that would be a pause of more than 1 second or 1 second and longer. Okay, 1000 milliseconds. If there was no keystroke event recorded in within 1000 milliseconds, then we would consider this to be a separation between two typing events. There are some reasons why we choose here 1 second, but there has a little bit of discussion in that literature. What is the reasonable value to assume, and why we would take 1 second and not maybe, for instance, 500 seconds, 500 milliseconds, or 2 seconds, or others talk about 5 seconds even. And so with these different kinds of pauses, we would assume to fragment different kinds of behavioral, I mean, or thinking processes, right? So if we say this is one translation unit that is characterized by a translation burst, by an output and a pause before, then we would assume that if this pause is to be 1 second or longer, we will assume that certain kinds of activities, mental processes take place, and different kinds of mental processes perhaps take place if we only assume this to be 300 milliseconds or 5,000 seconds and so on. And this exactly is the idea in these values here. So we have here the production of one segment. So each line is one segment. The production of one segment means, if you look again here, so it would represent whatever happens in one segment. So these vertical horizontal lines here are one segment, right? And all the behavioral data that was collected within in between these two lines, that would be represented somehow in this segment, in this SG table. Okay, so here we have, if we assume a translation gap means a pause of 300 milliseconds, then we see in this segment 42 translation bursts. Means, okay, so if we start with this guy here, 1000, this is what actually we see in this progression graph. In this particular segment here, there were 12 translation bursts, assuming that the burst is defined by a pause of 1 second or longer, okay? And these 12 translation bursts are make up 31 seconds. Means you can easily calculate, if you divide this, almost 3 seconds per translation bursts, okay? And the translation gaps, so the pauses between these translation bursts are, what is this? 10 seconds, right? If we assume that there is a translation burst is separated by a pause of 500 milliseconds, we come to this values. We see 21 translation bursts, and the total duration within these bursts is 25 seconds. And this is 100 seconds, right? So this is 100 seconds, 106 seconds, and here it's 100 seconds. And so on. And so this pre-gap here is the duration before the first keystroke. And this pre-gap in the second segment is the time between the last keystroke of the first segment and the first keystroke in the second segment. Okay, so means if that person goes from this segment, from segment 2, we're in segment 2 here, to that segment. So there's, at one point, there's a last keystroke here, okay? And the time between this last keystroke and the first keystroke here would be this pre-gap. So the time, the pause before the first keystroke, before starting the first keystroke. So we have different kinds of prefabricated pauses, and each of those with 3 different values, with the translation bursts, how many translation bursts we have, how much does the translator spend in the translation, and how much is the pause there. Okay, so that's these values. Otherwise, we have these fixation values. So we have 144 fixations on the source text, which adds up to 39 seconds altogether. This is the number of fixations and the duration on the target text. Then we have a concurrent parallel activity. Here is nothing. I don't know why. So here we have the insertions for that segment, the deletions, the number of source text tokens, the number of source text characters, target number of tokens, target number correct, the characters. This was the case if we had machine translation. Here is the actual translation that was produced. That's the string. And so these values we will discuss on another day when we talk about these entropy values and so on. Okay, so this is basically the features that are in the SG tables. These are summary information for each segment. Okay, now we can,
Michael,
of course.
I have a question, Michael.
Please.
You said at the beginning that these are the data coming from translation sessions in Trados.
Yes.
If we have another editor, like the translog editor, would we still get the same type of data?
Yes, yes, exactly. So that's basically the idea. So we have different data collection tools, Trados and Translog, but the tables will look exactly the same, so that we can compare data that was collected with different tools. That's basically the idea of this whole database, that we have thousands of sessions collected in different modes, with spoken and written and post-edited and whatever. So we have different modes, and which will then be here, okay, the T translation. But the features of the data tables are all exactly identical. So we can compare Trados and Translog data, and we can compare spoken data and written data and site translation and interpretation and whatever you can think of. So that's basically the idea of this database, to make these different kinds of data acquisition modes and tools, make it all compatible and comparable. Okay. Okay, so we can now look into histograms. Okay, here that's what we just discussed, and we can have different number of bins here. As you can see, it doesn't change very much. If we put 500, it takes a bit longer to produce this, but you can see this maybe not a very nice representation. It's too many bins, maybe. Because we only have 250 or so data points. It doesn't make sense to have more bins than data points, right? So if we have 100, then we have maybe on average something like 2 data points in each bin. Of course, it will be differently because they are all equally distributed here. But I guess with 50 bins, we get quite a good impression of the distribution of the data. We see that most most segments are produced in this duration here around, what is this, 100 seconds. And we have some outliers here that are 700 seconds. This is 10 minutes almost, right? For one segment. So this is clearly an outlier. Now we can also normalize we can normalize and transform this data in various different ways. For instance, if we log transform this data, then we will more likely. So this is this is a very long tail towards the right, and a steep goes up here. If we log transform this, we will more likely see something more an equal distribution of it. And then we can also normalize this by the number of tokens. And for instance, or we could even normalize this by the number of characters, right? So we also have the number of characters somewhere, length T, length S, right? So, but here we can normalize the data. So because each text or each segment, so we have segments here, it will have different number of words. Naturally, well, we can expect that if a segment is longer, it will take longer to produce a translation. And so we might want to normalize this duration by the number of source text tokens, or maybe by the number of target text tokens. And then we can log transform still this normalized version of it. And here we can, so this is a function from pandas to describe, so we get all these interesting values that I described earlier. So we have the number, the mean, the standard deviation, the min, the maximum, and here these would be the quantiles and the maximum. So we get all these values for all the features in this table here. And now we can, or we can also look into, oops, what happens here? Okay, I need to run this guy here first. And then I hope I can run this, and we see, so if we log transform the duration, right, it gets a slightly different shape than this one here. Or we can also look into the log transformation of the normalization based on the target, on the target side word number of words, and we get something like this, a more regular, more symmetrical distribution, or something like this, where there seems to be only one outlier here a little bit, but it looks quite symmetrical, right? So it's possible to transform this data to get to have a different shape. To often it helps in regression analysis to have better values, and because it's assumed to have this kind of symmetrical distribution. We can do here. We did this with respect to the duration. And okay, so then we can also look into the correlation of these different values. And that's what I showed previously here. Okay, so we have, of course, the correlation between this duration. These middle values are always identical. And here here we see the correlation between the duration and their different kinds of normalizations or log transformations. This is a person, or Pearson, I don't know how to pronounce this, correlation. But if we take this rank-based correlation, we talked about this yesterday a little bit, and you can see here that the values will be quite different, right? So means in the rank-based correlation, whether we log transform something or not does not change the correlation coefficient here, right? So these stuff here are log transformed, Yeah, so this normalized duration based on the number of target text words correlates with where is it? With the log transformed version of it, right? Just like this guy here. If you compare this again to this other correlation that we had before, we see that here these, I mean, it's quite a strong correlation still, but it's not one, right? And why would that be the case that we see why would that be that the rank-based correlation is 1 here? It's, well, anybody can guess, because the log transformation does not reshuffle the data points. The rank remains the same. It's just a kind of a log. It's a kind of log transformation, but it does not change the order of the data points. Does that make sense? No? Anyway, so if something is not, if something is not really a very nice Bell transfer or normal distribution, then people tend to use other correlation like the Spearman correlation here. So we can do the same with insertions here. Here we were talking about temporal, how long it takes, and we have different kinds of transformations for the temporal dimension. Here we can look into different kinds of keystrokes. So, for instance, we have a column insertions, the number of insertions per segment and the number of deletions per segments. We can just sum them up and have the number of keystrokes. And then we can also normalize this by the number of tokens, source text tokens, or target text tokens. So what would that mean? So we have a normalized number of insertions based on the source text token, even though the translator, of course, only types the target text, right? So what normalization would be more interesting or make more sense? Or here, so if somebody writes a very long version of a translation and another person writes a very short version of that translation, the normalization based on the target text, on the number of target words produced, would be, of course, very different from that of the source sentence, because the source sentence, if the source sentence is the same and you have two translators producing two very different translations, this normalization here would be different, but this one here would look only into the number of source text words, right? So this is normalized, so this this would normalize the production based on the number of source text words, and this one here based on the target text words. This is the same for the deletions. And then we can also, of course, log transform this, the normalized number of insertions and deletions. And then again, we can all correlate this, and we can see again here that okay, what you can see here, that the number of insertions and deletions, there's a quite strong correlation here. If translators insert more, then they tend also to delete more sentences, words, or have deletion keystrokes, and so on. So we can see this kind of correlation. Of course, we can also look here into the Spearman correlation, and we see, well, all these are similar transformations here. They don't change the order, but we see that in this Spearman correlation, the the insertion and deletion correlate less, right, as compared to before. No, better. So this is similar to what we looked into yesterday with this correlation, and then we can, of course, also have a scatter plot here, the number of insertions, and the number, the duration, the log duration based on the target text normalization, and we see that there seems to be a good correlation here, right? Between the number of insertions and the number of deletions. Now, if you look into this, so a correlation would just look into how well we can fit in a line here, and a linear regression would so would fit that line and explain how what is the intercept, means at what point this line here crosses the 0 point, and what is the slope of that line here, and these shades here would be an error margin. So the line could actually be a bit flatter or a bit steeper, but the line that is fitted here looks like this. So, okay, so we have here the number of the duration of the duration per word log transformed, and then the number of insertions. Okay, but remember we had here, when I loaded this data set, we have two different kinds of data sets. One is Spanish, okay, and the other one is Arabic. And we have these number of different sessions here. And now they are all merged together here, okay? So on average, we see this line. Now, if we disentangle this, then you can see, oops, actually, these two languages behave quite differently, okay? Means, so how would you interpret this, such a graph here? So this means, well, in both cases, we can see that the line goes up, right? Means that the more insertions there are, the longer the translator needs, but an Arabic translator would need much longer for more insertions, and the Spanish translator or translator into Spanish would have a slightly different behavioral pattern here, okay? So they would not need as, so it seems that if they produce more insertions, then they would not equivalently use more time as the Arabic translator does, okay? Now we can, so this is with respect to, so we can see here basically an interaction effect, right? So the two lines, if they were parallel, if these two lines were parallel, we could just say, okay, so an Arabic translator just needs a little offset more time, but here the two lines, the slope is different, right? And so there seems to be quite a different kind of a process, or it's an indicator that there might be a different, that it's much more difficult for an Arabic translator to produce longer sentences than for Spanish ones. Okay, so we can look at the texts instead of the languages, and here doesn't seem to make much of a difference, right? So some text are, the slope is a bit steeper, the other one is a bit flatter, but the error margin is quite big and overlapping, so that doesn't seem to be very interesting kind of results that we get from this here. Now, if we look at the participants here, okay, so we have 6 different participants, and here we need to know that 2 participants, I think, are Spanish and 4 are Arabic. But here we can see that 1 participant, this yellow one, is much quicker than the other ones. Okay, so they all seem to, you know, all the lines are more or less approximately parallel, but only this translator is quicker than the other ones, right? So we come to quite, depending on what part, what we look at in this graph, we come to quite different conclusions. Here we conclude that Arabic translators behave differently from Spanish translators, right? If we look at the participants, we can see, oops, this translator is quicker than those translators here. So we have a difference not between the languages, but between the individuals. And now we can, of course, look into all these things together, and we can separate the participant here from the target language from the text. And we can see here that, okay, so the text was not so interesting. I just take this out here. Okay, then it would make this whole thing a little bit shorter, I hope. Okay, so we see that the Spanish translators, we have 2 Spanish translators here, the blue and the yellow one, and these 2 lines are approximately parallel, and the yellow one is quicker, seems to be quicker than the blue one. And here are the Arabic translators, 4 of them. So 2 and 5, as you can see here, are Spanish, and 1, 3, 4, and 6 are Arabic translators, and they all seem to be so they all seem to have a similar slope. Okay, means that the impression that this one here gave us was actually misguided by the fact that we have 1 translator here who is very quick and the other one is not very quick. If we disentangle this, we can see that all translators behave a little bit similar, but only with an offset here. Okay, makes sense? Okay, so this is a visualization in Python, and then there is a package in Python that uses least square regression similar to R, and people who have used R will be familiar with this output here a little bit. We can basically put this formula inside this. We can put a formula here, and this formula looks very much like what people are used in R. R is very strong in regression models. And this is the stuff that we saw in the beginning. Okay, and the way this is to be interpreted here, we can see how well this model, so this model here, how much this explains the R square, which is not so bad, but it's also not really very good. And here, the interesting information here are these 2 columns here, I think, which is the intercept and the slope. So the intercept here means this is, the intercept is where this, where this slope crosses the 0 line. So the intercept is around 60,000. Yeah, this line, if we go this line, if we go further here, then this would be around 60,000. That's what this number says, 60,000. So this intercept means that if no keystroke is produced for translating a segment, then we already use 60 seconds, right? 60 seconds, 60,000 milliseconds is 60 seconds. So each segment takes 60 seconds, and for each insertion, another 600 milliseconds is used. Means that if we come here to 100 insertions, we have this 60,000 something plus 100 times 600. This is another 60 seconds, no? So this would be around 120, something like this, 120,000, right? So these are the two interesting values, I think. In particular, the slope here. That's the effect. Yeah. So how much? What is the impact of insertions on the duration? And we can see in this value here that both these values are significant. Okay, so we can say we can be quite confident that this is true. Yeah, so that or we can at least we can reject the idea with quite high confidence that insertions do not have an impact on the duration, right? That would be the zero hypothesis would be whatever insertions I produce or translator produce, it does not have an impact on the duration. And with this analysis, we can reject this. We can say this hypothesis that insertion has no effect on duration is with high probability wrong. And which basically means that it's likely that insertions have an impact on the duration. And you can see this in this slide here. Okay, and then we can go on and have this. We can use this normalized and this log transformed features, and we get some similar things. Or we can have a couple of different independent variables here. We can see what is the impact if we take these two variables, so namely the deletions and the insertions, and look at the impact on the duration. And here we can see that that if we add this variable here, okay, it does not have an impact, an additional impact on the duration. Yeah, so we have this p-value here is quite high, which means that we cannot reject. So this corresponds to this graph here, right? So we have this graph here and this graph here. So this is the impact of deletions on the duration. And even though it looks like there's a slight slope here, this analysis tells us, no, we cannot reject this null hypothesis.